Right, hello students. Today we will discuss the Euler's method. It is used for numerical differentiation. All right, so we will follow chapter number 25 from the book, chapter number 25, page number 727 of the book, Stephen C. Chapra. Let me show you the front page of this chapter. Here is chapter number 25. Okay, and we have got here page number 725. Okay, so we want to solve numerically, we want to solve numerically the differential equations, right? Ordinary differential equations. For example, you can see here, this is a ordinary differential equation. Okay, we can solve it analytically, but now today the concern is that we want to solve it numerically. There are three numerical methods that you will learn. Number one, Euler's method. Number two, RK2 method. And number three, RK4 method. Okay. RK4 method is better than Euler's and RK2 method. We will learn it when we experience these all methods, and when we implement the methods on some problems, you will see that the error will be very low when we use RK4 method, whereas the error will be high when we use the Euler's method. Okay, so now I have prepared some slides for the method understanding. So let us go through the slides. Okay, we use the Euler's method for numerical differentiation. How does the formula look like? The formula is dy by dx is equal to f of x pi. Now, what is this actually, students? I have a differential equation and I will just write ordinary differential equation. I will write the derivative part on the left hand side and the other parts on the right hand side. And I will say dy by dx is equal to f of x pi. Next, this is the formula for the Euler's method. Okay, you will remember this formula, and when I ask you to implement Euler's method, you will substitute the inputs in this formula. Okay, and we have already learned numerical differentiation, so we have derived this formula from the forward numerical differentiation. Okay, you can see we can replace dy by dx by yi plus 1 minus yi divided by h, and then by cross multiplication we can obtain yi plus 1. All right, next we have a method description with the help of an example. Consider I have a differential equation dy by dx is equal to y t cube minus 1.5. Now, students, it is very obvious that t is the independent variable, y is the dependent variable. We will use interchangeably t and x. So please do not be confused, all right? Here we are talking about time and derivative of y with respect to time. Now you can see the equation is separable, right? So I can put the y stuff on the left hand side and the t things on the right hand side, integrate it. I've got a constant of integration. For this, I need the condition. So we need to keep in mind the initial condition. Okay. So students, the initial condition was at t is equal to 0, y is 1. Okay, y of 0 is equal to 1 was the initial condition. Okay, so if I put here t is equal to 0 and y is equal to 1, you can see I can get c is equal to 0. So therefore this is the analytic answer. Now I want the numerical answer. For the numerical answer, we will use the iterative procedure. We will use the step size. You can see here that I have just showed you the results, but please do not worry. We will go through all these results in a minute. But let me show you the numerical answer here. What is happening here, students? I have kept the step size equal to 0.5. Now, what is this? Actually, I want to find the y. What is the plan actually? For example, a differential equation is given to me and I want to find y from this differential equation. Dy by dx is given and I want to find y. And how will I find it? I will discretize the domain, divide the domain into small parts with a pre-planned step size, okay, and obtain the y values at those discrete locations. Okay, So what is happening here? I have got, like, for example, T0, 0.5. This is very straightforward. This is only x naught plus h. This is x naught plus 2h. This is x naught plus 3h. And this is x naught plus 4h. Okay. So I have asked you to find y at x is equal to 0. And for this part, it will be given to you. The starting values, these are called the initial conditions. This will be given to you. This is x naught, this is y naught. X naught and y naught will be given to you. And we can write it as y of 0 is equal to 1. Okay, these values were given to you. Next, this is x1 and this is y1. Y1 we obtained with the help of the Euler's formula. I will show you how. Okay, so let me show you how. Now, students, what will happen? We will first identify the initial conditions. This is what I have showed you. For example, for this question, y of 0 is equal to 1 was given. Next, arrange the differential equation such that dy by dx is on one side and the rest of the terms are on the other side. Dy by dx is on one side of the differential equation and the rest of the function is on the other side. Okay. Next, we will see that what should be the next step. Obtain y2 with the help of x1 and y1. Students, do you remember I had the formula yi plus 1 is equal to yi plus h f of xi yi. Substitute here I is equal to 1. What will you get? You will get y2 is equal to y1 plus h f of x1 y1. Next, you can see that you will obtain, once y2 is obtained, repeat the procedure for y3. Okay, and if you are using the index, your index is starting from 1, then of course you will start from y2. For example, x1 and y1 is given to you, you will go to y2. If x0 and y0 is given to you, you will go for y1 first. Okay, but it is a chain process. For example, you will obtain y1 from y0, y2 from y1, and y3 from y2, and so on, y100 from y99. Okay, so this is the procedure. Now let us solve this example using the formula. Okay, I have the Euler's method formula as well, but let us just concentrate at the moment on the given problem. So let us read the question. And here is the question. The function is given as f of xy is given as y t cube minus 1.5. Okay, so let us type it here. I will say that I have, let's say, f t y, or I can say it any other name. I can give it any other name. So I will write at the rate t comma y, and then the function is t times y times t cube minus 1.5, y times t cube minus 1.5. Let's write it here. Y times t cube, let me double check. Yes, t cube minus 1.5, y times t cube minus 1.5. Okay, and I can now substitute here. For example, I can now substitute here. Okay, this is better because I haven't defined t and y yet. So it is better to write it single f, okay, in the MATLAB language. So I have here ty as y t cube minus 1.5. This is the f of xy. Now, students, what is x? We have said that x starting value is 0 and the step size is 0.5 and the ending point is 2. Now, all these steps you can do using a paper and a pen. There is MATLAB is not compulsory for this lecture. For the upcoming lecture, it is compulsory. All right. So here I'm just doing the calculation using MATLAB because I can do it very swiftly. That's why. Okay. So I want to show you X data points, and I'm expecting that I will get 5 data points. Let's see, 0, 0 0.51, 1.5, and 2. Okay, students, now I want the y values, but only y1 is given to me. Okay, so let me say that x1 is, of course, x1 is 0 and y1 is given to me. Okay, I'm saying y1 is 1. Okay, so the point is that what is functional value at these points? For example, y times t cube and minus 1.5. Okay, so I want these values, and I can see here a dot static is missing. I've now corrected it. Now I want f of 0, 1. Okay, and let me check here at ty. Okay, here I will put the value of t, here I will put the value of y. Okay, let's hope that it works. The answer is minus 1.5. Okay, and here I can see that dy by dt is equal to f of ty, which is minus 1.5. Okay, now this is the first step. Now I have obtained x1. I can show you where is x1. Remember, this is x0, x1, x2, x3, x4. Okay, now students, I have obtained x1, which is 0.5. I have obtained y1, which is what? What is y1 actually, students? Let us go to the formula and let us take a look. It says that, the formula says that, here you can see, here is the formula. Formula says that yi plus 1 is equal to yi plus f of xi yi h. So actually what is happening here, students, I am talking about y1. So put I is equal to 0 in this formula. What am I asking you to do? On your notebook, substitute here in equation 2, substitute I is equal to 0. What will you get? Y1 is equal to y0 plus f of x0 y0 h. Okay, so actually what is happening here, you are saying that if you want y2, now because MATLAB will only believe in the index, like index from 1, 2, 3, 4, not for 0. Okay, so you have here, for example, if I want to go to y1, how will I write the formula? For example, here you can see I'm saying x1 and y1 is given to me. So actually I'm saying that here I'm using the index 1, 1. So I must say that now I will go for 2. Okay, so I'm saying y2 is equal to y because MATLAB index is strictly for starts from 1, not from 0. Okay, so f of x1 y1. Okay, so now I'm saying that instead of substituting 0, if I substitute 1 here, what will happen? Y2 is equal to y1 plus f of x1 y1 h. Okay, so let us go to this step to obtain y2. Okay, so now I'm going to substitute these values. I will say y2 is equal to, what is y1, students? I have mentioned here what is y1. Y1 will be given to you, 1. Okay, so you will have 1 is y1 plus h is 0.5 and f of x1 y1 is actually this thing. F of x1 y1 is this value at x1 or t1 is 0, y1 is 1. Substitute 0 and 1 in this function. You can see here that you will obtain this value. Okay, so you have got here for t substitute 0, for y substitute 1, minus 1.5. Okay, so I will substitute here minus 1.5. Okay, so I have got y2 is equal to 0.25. Let us compare the answer. Here you can see y2 is 0.25. Now you can go to y3. Let us go to the third step. For y3, I need x3. Let us go to the x data. This is x1, 0. This is x2, 0.5. This is x3, 1. Okay, now I am using the index 1 instead of 0. Okay, we will strictly use the index 1. So 1, 2, 3. x3 is given to you as 1 because the step size was 0.5. So now we have x3 is equal to 1. Now I want y3. So the formula for y3 should look like y3 is equal to y. Let us write the formula for your better understanding. Formula is y3 is equal to y2 plus h times f of x2 y2. Remember this, students. Okay, so now I want to find y3. I will say y3 is equal to y2. I know y2 is 0.25. It is given, plus h 0.5 times f of, yes, what is x2? X2 is 0.5. What is y2? Y2 is 0.25. Substitute, students, or if you are using paper and a pen, substitute here in this formula. Here, for t substitute 0.5. For y substitute 0.25 because these are the values for x2 and y2. All right, so now my y3 is 0.0781. Look at the table here. Look at the answer here that I've got 0.0781. Good. Now we can go to the fourth step, and after that we will change the step size. So now students, what is x4? X4 is 1.5 and y4 is actually, yes, y4 is actually, let us correct it from here. Y4 is actually y3 plus, the step size should remain the same here in this question, 0.5 times f of, yes, f of x3 y3. What is x3? 1. What is y3? It is given to you here 0.0781. So it is up to you if you straight the way write here y3 or you write here the value, does not matter. So let us this time do it this way, x3 and y3, f of x3 and y3. This is y4. Let us compare the answer here. This is y4, 0.0585, and here I have got, because I am rounding it to 4 decimal places, that's why 0.586. All right, now students, this that is it. Now you can even go for y5 for 2 and you can obtain this value 0.113525. Now the next part of this question is that we want to solve this problem for the step size h is equal to 0.25. Now, always remember that for your future studies as well, that whenever the step size is small, the numerical results are better. Okay, what did I say? I said whenever the step size is better, step size is small, the numerical results are better. Now, part C is that reduce the step size to 0.25. Okay, now x will change. So I have 0, 0.25, and 2 is the ending point. Now students, I have got 9 values. Okay, lot of work, right? So now I will write the formula here. X1 is this time 0 and y1 is 1. This is the initial condition, strictly shall remain the same. Okay, so now I have y2. Y2 is y1 plus h dot static f of x1 y1. So let us hope that we get the correct answer. I forgot to mention h. H is 0.25. Right. So y2 is 0.625. Okay, let us compare the answer here. Wow, y2 is 0.625. Good. Now let us go to y3. So let me write the formula here. Right. So let us make it standard formula. I will say h, and then I will say y2, and I will say x2. Okay, so I'm saying x2 is, let me mention, okay, otherwise I will get the error. X2 is this time, what is x2? X1 was 0, x2 was 0.25. The step size changed, that's why. So 0.25 is x2, and then y3 is y2 plus h, f of x2, y2, right? So y3 is 0.3931. Okay, because we are rounding it to, in MATLAB currently I can increase it to more decimal places, but for better accuracy, and even it is allowed to you as well for the exams, up to 4 decimal places is acceptable. Okay, 0.393. Okay, now I want you guys to solve this question. Okay, and another question for 2 step sizes. All right, and I will look forward for your answers. And after that, there will be a one-to-one session for every student, a Viva, okay, 5-minute Viva. I will talk about the details later, okay? So please go through the question, and next week I will share with you the M file.